Hey guys, it's Miss Johnson, and I'm here to bring you our first part of section 12.2. Today we're talking about chi-square tests for homogeneity. That's what that word is, homogeneity. So we talked about chi-square in 12.1 and how chi-square is a test for categorical data. So we're still looking at categorical data, but now we're going to start comparing two populations with each other. So we're just going to start by looking at what those hypotheses would look like. So if I were going to write a hypothesis for a situation, it says, does background music influence what customers buy? One experiment in a European restaurant compared 3 randomly assigned treatments: no music, French accordion music, and Italian string music. Under each condition, the researchers recorded the number of customers who ordered French, Italian, and other entrees. So the null hypothesis is that there's no difference in the true distribution of entrees ordered at the restaurant when playing the music, the different kinds of music. And the alternative hypothesis is that there is a difference in the true distributions. So what we're looking at here is we're looking at the variable of music against the variable of type of food ordered. Okay, so this becomes a two-way table. We're going to get back into two-way tables here, and we're looking at comparing these two variables together. We want to see if one is affecting the other. So one thing to caution you on, it says the alternative hypothesis does not state that each distribution is different from each of the others. It just says that there is a difference in the true distribution of entrees. All right, so here is what the two-way table looks like. So here's your data. You've got the type of background music, none, French, Italian, and you've got the type of food, French, Italian, and other. So then you can see that they took those two-way tables and they put them into distributions. They showed you bar graphs of the distribution. So you can see that for no music, the greatest thing was other. For French music, French food was ordered more, and for Italian music, other was ordered more again. So you can just see a picture of the distribution from that two-way table. So the question is this graph different enough from this one and different enough from that one to be statistically significant? Do the differences in these distributions provide convincing evidence that the background music affects the customer behavior at the restaurant? Is it affecting the food they're choosing? Or is it plausible that the background music has no effect on the customer behavior and that the differences are due to chance involved in the random assignment of the treatments? So we can compare many pairs of the proportions ending up with many tests and many p-values, but this is a bad idea. So what we do instead is we perform a test of homogeneity. So it says performing multiple tests on the same data increases the probability that we make a type 1 error in at least one of the tests. So if we were going to test this versus that, or this versus that, or this versus that, or this versus that, that's just a lot of tests going on. We don't want to do that. So when we use a chi-square test for homogeneity, we kind of look at the whole big picture all together. So the problem of how to do many comparisons at once without increasing the overall probability of type 1 error is common in statistics. Statistical methods for dealing with multiple comparisons usually have 2 steps. Perform an overall test to see if there's convincing evidence of any differences, or when the overall test shows there is convincing evidence of the difference, perform a detailed follow-up analysis. So you can do the overall test, and then if you do find that there's a statistical difference in general, then you can break it down and go further, okay, and decide which of the parameters differ to estimate how large the differences are. All right, so now let's talk about expected counts, because we also need to compare. We need to know what to compare these to. So we're going to have the actual data, but we also want to look at the expected counts. So it says test for homogeneity, expected counts in the chi-square statistic. To find the expected counts, we start by assuming the null is true. So we're going to assume that there's no difference. In the purple box, it says if the specific type of music that's playing has no effect on the entree orders, the proportion of French entrees ordered under each music condition should be 99 out of 243. So if you're looking at, this is where we would get into those proportion values to see if they were independent from each other or not. So if you were going to compare each one of these, it needs to equal this proportion because that's the ratio of French ordered food to all of the ordered entrees. So basically what they're saying is that 30 out of 84 needs to be equal to 90 out of 243. Okay. So because there were 84 total entrees with no music playing, we would expect that 84 times that proportion, or in other words, 34.22 of those entrees would be French on average. So the expected count for this number right here is 34.22, but the actual data gave us a 30. So then the question is that statistically significant of a difference? So here's the table of all of the expected values. If you take 99 out of 243 and multiply it by 84, you get the 34.22. You multiply it by 75, you get the 30.56. Multiply it by 84 again, you get that 34.22 again. If you take the 31 out of 243, 31 out of 243 times the 84 in this column gave them the 10.72. 31 out of 243 divided or times the 75 in this column gave them 9.57. So that's where those expected counts are coming from. And here's kind of your little equation for that. All right, so here's your AP exam tip, the first of many in this section. It says, as with chi-square tests for goodness of fit, the expected counts should not be rounded to the nearest whole number. While an observed count of entrees ordered must be a whole number, an expected count need not be a whole number. The expected count gives the average number of entrees ordered if the null is true and the random assignment process is repeated many times. So if the random assignment process is repeated many times, then it's possible for you to have an expected count that is not a whole number. All right, so here's where we get into counting the chi-square test statistic. Now, we saw this yesterday, or we saw this in 12.1, I should say. We saw the chi-square test statistic being the sum of the observed minus expected squared divided by expected. That is still going to be true for tests for homogeneity. So chi-square for this would be 30 minus 34.22 squared divided by 34.22. Basically, they're going to add that up for every single cell, every row and every column, aside from the totals. You're doing just the data. So every row and every column gets this piece added up, and you get a chi-square statistic of 18.28. So it says in the do step, you don't have to show every single term in the chi-square test statistic. That's not realistic. So notice right here, they showed 1 and 2, and then they did the plus and then an ellipsis, and then they did the last one. Just show a couple of them. I've seen where they even only show 2 of them. You don't have to show every single one, okay? So if you write the first few terms and sum and followed by the ellipsis, that's considered showing your work. So we suggest you do this and let your calculator tackle the computations, because the more you try to enter into your calculator, the more chance you have of making a mistake. So you don't want to do that. All right, so here's our first question of the day. It says, for a class project, Abby and Mia wanted to know if gender of an interviewer could affect the responses to a survey question. The subjects in their experiment were 100 males from their school. Half of the males were randomly assigned to be asked, would you vote for a female president by a female interviewer? And the other half were asked the same question by a male interviewer. The table shows the results. So we're going to state the null and alternative. We're going to show the calculation for the expected count, and then we're going to calculate the value of chi-square. So the first part, state the appropriate null and alternative. Okay, so here's where you're going to do the bulk of your writing in these questions. Stating these null and alternative hypotheses are often very wordy. So my null would be that there is no difference in the true distributions of response to this question when asked by a male interviewer, and when asked by a female interviewer. And here's where we need to be careful because we're assigning a treatment here. So we need to say in subjects like these. Like these. Because this is a treatment, we've used every person that was involved in the experiment. So we have to state that we're going to generalize this to the broader good of people who are like those that are in the survey. So here's all our alternative, and literally it's going to be one word different. There is a difference. And if you're asking me if you have to finish it out, the answer is yes, you do. So there is no difference, there is a difference. And then finish it out. The rest of it is literally the same. In the true distribution of responses to this question, I keep dragging my letters together, sorry. Question, when asked by a male interviewer and female interviewer in subjects like these. I want to remind you that yes, this is a lot of writing, and yes, it's going to take you a while to write out all these hypotheses, but remember that the AP exam is not a grammar test and it's not a spelling test. They cannot dock you for grammar and they cannot dock you for spelling. All right, so let's look at B. So show the calculation for the expected counts in the male yes cell. So they just want you to show the expected counts for one of them. So male and yes, okay? Here's where we have to look at what is the total divided by the total number of people. So the total yeses divided by the total number of people. 69 out of 100 is 0.69. And then you take 0.69 times the 30, or I'm sorry, times the 50, and you get 34.5. So for male and yes, and sorry, I was typing that into my calculator at the same time I was talking to you, so that's probably why you're wondering, what is she doing? So for male and yes, we would take 50 times 69 out of 100, and that would be 34.5. Then it says provide a completed table of the expected counts. So if I set up a table here, I've got, I'm just going to make my table look very similar to theirs. Expected counts, gender of interviewer, and I've got male, female, total. So, and then you've got yes, no, and total. Okay, so we already did this first one here. This first one up in the top left is 34.5. And lucky for us, we have an equal number of male interviewers as we do female interviewers. So that means this one is also 34.5. And if you add 34.5 plus 34.5, you get that total of 69. So that one's good. Now let's look at the next one. Oh, I missed the maybe column. Sorry. I'll put my maybe row there. So now let's look at the next one. So now I need to take a look at 11 out of 100, which is 0.11. So now do 0.11 times 50. 0.11 times 50, and that's going to give me 5.5. And if I do add 5.5 plus 5.5, I do get 11, so that's good. Now let's take a look at the maybe. That was the one that I missed, sorry. So maybe you got 20 out of 100, which is 0.2. So 0.2 times 50 is going to be 10. You get 10. 10 plus 10 is 20. And if I added those up down at the bottom, 34.5 plus 5.5 plus 10 does in fact give me 50, and it's the same for both. 50 and 50 is 100. Okay, so this is what my expected counts table would look like. So now let's take a look at the chi-square test statistic. So if I'm going to calculate the chi-square test statistic, I would have to look at each individual cell, and I'd have to do the actual data minus the expected data, and then square that and divide it by the expected count. So my chi-square looks like this. This is part C. Let's just do this first cell. I'd have 30, and then minus the expected count that was 34.5, square that and divide it by 34.5. If I do the next one over, or let's say I do the next one down, I would have, that one was 5.5. So I'd have 8 minus 5.5 squared divided by 5.5. Now here's where you can do plus, put your ellipsis in, plus, and get the whole chi-square test statistic at the end. Here's where you're also going to be able to put this into your calculator. So let's look at some calculator keystrokes. So on your calculator, I want you to, this is TI-84, I want you to hit second and then matrix, which is on the left-hand side, the fourth button down. For me, it's the fourth button down, so second matrix. Then you need to arrow over to edit. So we're not putting this in our stat editor, but we're putting this in a matrix editor, which is going to be really similar to what stat editor would look like. So I have a 3-row by 2-column. So I'm going into matrix A, and I'm making it 3 by 2. Because all you want to enter is your data. You don't want to enter the totals. So you're not going to enter these in the matrix. You're going to just enter the raw data. So then just go through and enter it in. My first column is 30, or my first entry is 30. And then when you hit enter, it goes over to the next cell. Then you hit 39. Then you put in 8. Then you put in 3. Then you put in 12. Then you put in 8. So I'm entering my actual data. Put the actual data in your matrix. Okay, so enter your actual data into your matrix. Now, next thing, you're going to go to stat, and you're going to arrow over to tests, and you're going to arrow down to, for me, it's option C, but it says chi-square test. It's not the GOF that we used the other day. It's not the goodness of fit test. It's the actual chi-square test. And you'll see that it asks you for a matrix. So your observed values are in matrix A. That's where mine are. You don't need to do anything with the expected values. They're going to calculate the expected values. And what it's telling you there is that the expected values are going to go into matrix B. Then you go down and you calculate. And look at that. You end up with a chi-square value of 4.24. You also get the p-value of 0.119, and it tells you the degrees of freedom is 2. So those are the 3 things that you're going to be needing for this data. And we're going to talk about how they get the degrees of freedom because it's interesting with a two-way table here. All right, so as I'm sure you're not surprised, but there are conditions that we have to find with tests for homogeneity. They're the same as before. So you need to know the data comes from random samples. You look at 10% when you're sampling, not when you're doing an experiment, but when you're sampling. And then the large counts need to all be at least 5. And that's the same as they were in section 12.1. All right, so now let's look at a new question. It says in the preceding example, you read about an experiment to determine if the gender of the interviewer affects the responses to the question. Would you vote for female president? Here are a table showing the observed and expected counts. So here is the raw data. Here's the actual data. Here are the expected counts, okay? So earlier we calculated that the chi-square test statistic was 4.25. First of all, we're going to verify that the conditions are met. Then we're going to look to find the p-value. Then we're going to interpret the p-value, and then we're going to make a conclusion. So let's talk about conditions. So in conditions, do we have random assignment? Yes. Okay, the subjects were randomly assigned to the treatment. Then this was an experiment. So we do not need to talk about the 10% condition because we used every single person in the experiment. But we do need to look at large counts. So from large counts, you need to look at the expected counts and make sure that they're all above 5. So you're looking at this data right here, and they're all good. So all expected counts are greater than or equal to 5. That's a check. That's a check. And you would put something like C table above, C table of expected counts, to reference that you're looking at those values. And again, we don't need 10% here because we assigned things to treatment. Okay, so now we're going to look at part B. It says use table C to find the p-value and use your calculator's chi-square CDF command to find the p-value. So we're going to look at the p-value in both ways. Let's talk about degrees of freedom. Okay, so here come your degrees of freedom. When you have a two-way table, you need to multiply the n-1 for both variables. So the response to the question has 3 options. So you take 3 minus 1 for your number of options. And then the gender of interviewer has 2 options. So you take 2 minus 1 for those. And you end up with 2 times 1, which is where we get 2 degrees of freedom. Okay, so your degrees of freedom are 2. So you have to multiply. This is n times minus 1 for first variable and n minus 1 for the second variable. So n1 minus 1, n2 minus 1, if you will. And you multiply those two things together. That's where you get your degrees of freedom. So then when we go to the table, if you look at table C, you would go to the second degree of freedom row. You'd go to degree of freedom 2, and you'd arrow over until you found where does 4.25 fit. And you would see that 4.25 fits somewhere between 0.1 and 0.15. Okay, that's where 4.25 lands. So that's as close to a p-value as you get when you use the table. Now, we've talked about how that's kind of an outdated practice. So we're going to use the chi-square CDF command instead. So using technology, I want to go into the second distribution, and I'm going to look for that chi-square CDF, so cumulative distribution function. We've talked about Z-CDF, we've talked about T-CDF, we've done a lot of CDFs already. So this is chi-square CDF. So chi-square CDF, second distribution, chi-square CDF, my lower bound. So if I'm going to write this out, you've got chi-squared CDF. Remember that you need to include what all of these values are. So my lower bound is the 4.25. And the same things apply that we learned yesterday. We're looking at a right skewed distribution. We're looking at chi-squared. The bulk of the data is to the left. You've got a right tail that trails off. So everything starts at the chi-square value and goes up to positive infinity. That's how it works here for chi-square. So you're going to have a lower bound of 4.25, an upper bound of positive infinity, and then you always have to list your degree of freedom, which is 2, and you get a p-value of 4.25, was it 4.25 or 4.24? Yeah, 4.25. Upper bound, I just put in 1 and a whole bunch of zeros. Degrees of freedom is 2, and you get a p-value of 0.119. So p-value is equal to 0.119. Okay, and that is consistent with what we found in the table. 0.119 is in between those two. All right, let's talk about C. How would we interpret this? What does that p-value actually mean? So in C, remember when we're interpreting a p-value, we always start by saying, assuming the null is true. Then we say there is a 0.119 probability of observing differences in the distributions of responses as large as or larger than those in this study by chance alone. So what we're saying is that this is the probability that there was a difference. So if we were to do this again with any other subjects that are like the ones in the study, we have this probability of observing differences as large as or larger than the ones in this study just by random chance alone. Okay, so then the last one, what conclusion do we draw? This is where we would compare to a p-value. So let's talk about comparing to a p-value. If we use alpha equaling 0.05, what does that mean for us? So because p equaling 0.119 is greater than alpha equaling 0.05, we fail to reject the null. Then put it in context. We do not have convincing evidence that there is a difference in the true distribution of responses to this question when asked by male or female. In subjects like these. Interviewer for subjects like these. And yes, you're going to write a lot. Remember, not a grammar test, not a spelling test. As long as they can follow what you've written, you're doing great. All right, so here are the keystrokes for that calculator stuff that we went through. So the first thing you would do is you go to your second matrix. And then, and that's where you'd go over to edit and put in raw data. Not the expected counts, the actual data. Then you go to the chi-square test. So this is where you hit stat and then go to tests and chi-square test. And then you tell it your data is in matrix A. So here's the output. Then this right here is important because this is going to help you. So this right here, you get this by going back to second matrix and then go over to edit and go down to edit B and hit enter, and it's going to show you what's in that table. These are the expected counts right there. So this saves you a lot of time. You don't have to calculate those expected counts all on your own. It saves you a lot of time if you go back to that matrix and do it by yourself. All right, you guys, we're getting there. Now we're going to do one of these bad boys all the way start to finish with a whole chi-square. So here's your next AP exam tip. It says, of course, you can use your calculator to carry out the mechanics of a significance test, but there's risk involved. If you just give calculator without showing work, one or more of the entries is incorrect, you'll likely get no credit for the do step. We recommend writing out the first few terms of the chi-square calculation, put the ellipsis in. This approach may help you earn partial credit. You can get at least a P, even if it's wrong. Also make sure that you name the procedure. As always, like all of these things are the same things that we've been doing. And then you report all of the data, chi-square test statistic, degrees of freedom, and p-value. So all of these things are things that we've been doing all the way back since chapter 8. This is no different. You just keep doing all those things. All right, so here's your official box of what the chi-square test for homogeneity would be. We're looking at two different values. It says categorical variable of several populations or treatments. Okay, that's the key word there. When we get into chi-square test for independence, that's where things are going to be different. So several, when you're looking at more than one population. All right, let's do one start to finish. Pew Research Center conducts surveys about a variety of topics in many different countries. In one survey, it wanted to investigate how residents of different countries feel about the importance of speaking the national language. Separate random samples of residents from Australia, United Kingdom, and United States were asked many questions, including the following. Some people say that the following things are important for being truly, and then, Australian or whatever. Others say they are not important. How important do you think it is to be able to speak English? The two-way table summarizes the responses to the question. Do these data provide convincing evidence at the alpha 0.05 level that the distributions of opinion about speaking English differ for residents of Australia, UK, and US? Okay, so here are your two variables. Your two variables are what country are they from and how did they answer? They think speaking English is very important, somewhat important, not very important, not important at all. Okay, there's your data. Perfect. All right, so here we go. Now we're going to actually do the whole test. So we start by state. What's our HO? This is where you're going to have a whole lot of writing. So there is no difference in the true distribution of opinion that speaking English, or about, I should say, about speaking English for residents of Australia, UK, or US. And then the alternative, here's where you change one word. There is a difference in the true distribution of opinion about speaking English for residents of Australia, UK, and US. Okay, state, done. Plan. There's a lot going on in the plan part because you need to list the conditions, but you're also going to have to put in the table of expected counts. But I'm going to tell you how to make your life easy. So gear up. Get ready for that. Okay, so first of all, random. Okay, these were independent random samples. Notice the word independent. That's important. Independent random samples from US, Australia, and UK. Okay, check. 10%. This is a sampling thing. Samples. That means we have to address the 10%. So, here's where you're going to get into the total number of people surveyed. So I would say 1,000 is less than 10% of all Aussies. I'm going to abbreviate there. 1,460 is less than 10% of all UK residents, and 1,003 is less than 10% of all US residents. Okay, check. All right, so now let's get into the large counts. Here's where you need to look at the expected values. So this is data, right? We need expected values. So you're going to need to make a table. Yes, you're going to need to make a table. You're going to give the expected counts of the country responses. So you're going to have Australia, UK, US, total. Then down here, you're going to have very important, and I abbreviated because I don't have a whole lot of space. Somewhat important, not very important, and not important, and then total. So I'm going to have to write really small here, and I apologize, but it'll be okay. But guess what we're going to use to help us? Our calculator. So here's where I want you to go into your calculator, and you're going to actually just do the chi-square test statistic right now, because that's going to give you the expected count table so that you don't have to do the expected count table all on your own. So go to that second matrix, go over to edit. You're going to edit matrix A. You have 3 columns. You have 4 rows by 3 columns. So 4 by 3, and then type in your actual data values. So 690, 1177, 702, 250, 242, 221, 40, 28, 50, 20, 13, and 30. Okay. So there's my matrix for that two-way table. Now go into your stat test and go down and find that chi-square test, which is option C for me. My observed data is in table A. That's where I put it. I want my expected to go in table B. Yep, sure. Okay, so you've got the chi-square and the p-value and the degrees of freedom. If you want to go ahead and write those down right now, you can. But what I want you to do is go back to that second matrix option, go over to edit, and go down to B and hit enter. And now here's where you're going to see all these values. So I get 741.8, 1083.1, and 744.1. Then down the next row down, I get 205.9, 300.6, 206.5. Then the next row down, I get 34.1, 49.7, and 34.2. Then last row, I get 18.2, 26.6, and 18.2 again. Then you could go through the exercise of making sure these all add up. I usually just spot check the decimals, and then that kind of leads me to believe I'm doing okay. 9 and 1 is going to give me a whole. 8 and 2 is going to give me a whole. 8, 1, and 1 are going to give me a whole. Do you see what I'm looking at? I'm looking at the decimals there. So the totals are going to match your totals that you already saw. So this is 1,000. This is 1460. This is 1,003. There was a total of 3463. Does that say 63? I think. Yep. 25, 69, 7, 13, 118, and 63. So I didn't go through and spot check these, but you could. You could add and add to see that it equals the total at the end. It should be true for every row and every column. Okay. But guess what? You have to include the table. You sure do. So use your calculator to do all of that calculating for you. I don't want to sit and calculate all those. I don't know about you, but I don't want to, so I'm not going to. I almost forgot to address the large counts. So let's go ahead and actually address the large counts. So all expected values or expected counts are greater than or equal to 5. And that is true. I don't see any that are less than 5. The smallest one is 18. So we're good. Okay, that was the plan. Now we get to do the do, but guess what? We already calculated the do. So here's how you do the do statement. So first of all, show your degrees of freedom. You've got 4 options in that variable and 3 options in that variable. So you're going to do 4 minus 1 times 3 minus 1. That's 3 times 2, which means your degrees of freedom is 6. Okay, great. Then do your chi-square. So here's where you need to show just a couple of them. You don't need to show them all, but just show a couple. So I've got, the first one would be 690 minus that 741.8 squared divided by the 741.8. Then I'm going to do plus, dot, 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 plus, and I'm just going to do the last one. The last one would be 30 minus the expected counts of that cell. So 34.2 squared divided by 34.2. Now, go back to your calculator. If you cleared out your screen, it's okay. Just go ahead and calculate the test again. It's no big deal. Go stat, tests, go down to find the chi-square test. Your matrix is in A, hit calculate, and here's your chi-square test statistic, 68.57. Okay, so there's chi-square. Great. Check out that p-value. What in the world does that mean? And yes, you can list it that way. Mine says 8.02 times 10 to the negative 13th. That's scientific notation there. Okay. Yep, that's a real low p-value. Basically 0. Basically it can't happen. Basically this shouldn't have happened. Okay. So now, and actually you could even approximate this as 0, because that's how we're going to approximate it in our conclusion. So now let's actually make that conclusion. So conclude. In our conclusion, now let's address the p-value, because the p-value of approximately 0 is less than alpha equaling 0.05. We reject. We strongly reject here. We reject the null. We have convincing evidence that there is a difference in true distribution of opinion about speaking English in Australia, UK, and US. Oof, there's our conclusion. Holy buckets, you guys, we made it to the end. Here's our last AP exam tip for today. Many students lose credit on the AP exam because they don't write down and label the expected counts in their response. It isn't enough to claim that all expected counts are at least 5. You must provide clear evidence. So that's where I said, make the table. If you're not going to make a table, then you got to list them out. I see. And very important, equals blah, which to me sounds awful if I'm going to go through and make a list. So instead, you're going to make the table. We made it to the end, you guys. Chi-square test for homogeneity. Thank you for tuning in. I appreciate you making it all the way this far, and I will catch you next time.